All right, in this next example, we're going to look at graphing an antiderivative. All right. Now, again, watch what this is. We're using capital F and lowercase f, so you have to be a bit careful here. But let's say that we have f, a function f, capital F, and that capital F is an antiderivative of lowercase f. All right, so what is that saying? What is that saying exactly? That's telling us that, you know, if capital F is an antiderivative of f, then the derivative of the antiderivative should give us back the function, right? So that's telling us basically that the derivative of capital F is f, okay? So, and so this lowercase f is a rate of change function. It's a derivative. So the function f gives us the slope, right? It gives the slope. Gives the slope of capital F at any point. Okay? So, let's take a look at what that means. If lowercase f is greater than 0, right, that's telling us that the slope is greater than 0. So if the slope is greater than 0, slope is positive, right? So that means that the function, the original function, all right? So remember that lowercase f is the derivative, f is the antiderivative. So the antiderivative is increasing, right? Because the slope is positive, right? This lowercase f is our antiderivative, or sorry, is this lowercase f is the derivative if uppercase f is the antiderivative. Okay, so if the lowercase f is greater than 0, then the slope is positive, and the antiderivative is increasing on that interval. If lowercase f is less than 0, so again, negative, so the slope is negative, right? Because lowercase f is our slope, right? It's our derivative function. It's the derivative of the antiderivative. So, and so that means that the antiderivative is decreasing on that interval. And if lowercase f is equal to 0, right? So that's our slope. That means that's the slope of the antiderivative, right? Because it's the this is our rate of change function, right? Lowercase f is our slope. It's our rate of change. It's our derivative. Then the antiderivative is constant on that interval. All right, so let's take a look at, this just gets really confusing. I think it's easier to look at an example. So in this example, we're given the graph of f prime of x. Okay, so we're given the graph of a rate of change function. Okay, and we want to graph the function, sketch a graph of the function f of x. So essentially we're graphing the antiderivative. Now I kind of like this notation a little better because it's a little more clear. We're going to find the original function. We want to find information about the original function. All right, from the graph. Now we're also given some initial conditions here. We're given that f of 0 is equal to 10. So what I'm going to do, I'm just going to create a table of values, right? Before I sketch anything, I'm going to create a table of values, and I can also use the fundamental theorem of calculus to help me out here. And I'm given that f of 0 is equal to 10. So I can start there. And then I'm given some areas, right? This graph of the derivative, I got the areas, right? So that area is giving me the total change in the function, the original function, okay, f of x. So if I want, it looks like the first area that I'm given is the area from under the curve from 1 to 2. So I'm essentially given the integral from from 0 to 2, right? So if I want f at 2, right, then I can basically take f at 0 and add the integral from 0 to 2. of this f prime function, dx. All right, and I'm given that it's equal to 14, right? So I'm just going to take 10 plus 14 is equal to 24. So that's the value of the function at x equals 2. All right. The next area I'm given is between 2 and 5. So let's compute the value of the function at 5. All right. So I can take 24, take the value of the function at 2, and then add the integral from 2 to 5 of f prime of x dx. Okay. And that area is 20, so 20. Oh, but I have to be careful though, right? Because notice that this is below the curve, right? So this area is actually a negative 20. So I have 24 minus 20, which is 4, right? Because this is negative area. Negative area. And then, let's see, I can also, I've got the area given between 5 and 6. Okay, so I can compute f of 6. So I will just take 4 and add the integral from 5 to 6. Oops, I'm going to add the integral from 5 to 6. Hang on, I got to put a plus sign in there. Integral from 5 to 6. Okay, of f prime of x dx. All right, so that is now a positive area, positive 12. So 4 plus a positive 12 gives me 16. Okay, so now I have some points. I have some points that I can graph. So I'm going to scroll down here so I can, because I want to sketch a graph of this function. All right, so I've got some axes here, and now I can plot these points that I found. So I know that f of 0 is 10, so I'm just going to plot that point. I know f of 2 is 24, which I calculated, based on the fundamental theory of calculus and using the areas that were given. So at 2, we're at 24. So I'm going to say, okay, there's a point there. And then at 5, we're at 4. Okay, so we got a point here. Oops, maybe it's a little down, a little bit lower down here. If that's 5, let's say that point is 5, 4. Maybe I should label these points. This is the point 2, 24, and this is obviously the point 0, 10. So I don't need to label that one. And then also at 6. At 6, we're at 16. So let's say that 16 is about there. So 6, 16. All right, and our function does something in between there, right? Now I know that I can also look at, this is a derivative, right? So I know that the derivative is 0 here, right? That the derivative is 0, which means that the slope is 0, right? Okay, so and so I've got something that's going to come up here, and it's going to flatten out there, right? So essentially that's a critical point, right? This is a critical point. Critical point. And you can see that the function, this is again the derivative, so the slope is going from positive to negative, which means the function is going from increasing to decreasing. All right, so that's also a local maximum. All right, so then so it's curving around here and coming down, and so now the area, or where it's decreasing, right? It's because the slope is negative. And then we come back to 0 here, all right? So again, the slope is 0 here. So it's going to come down and go something like this. I'm just kind of sketching this in here and then come back up. Okay. All right. So we have a graph that kind of looks like that. If I can try. I don't know. I'm not very good at drawing with this pen here. All right, so there's a sketch. That's a sketch. Now I can also actually look at the concavity of this function. All right. Now maybe before I go on to that, let's answer some of the questions that they asked us. We're asked to sketch a graph and then also give the coordinates of the local maxima and minima. So we already saw that we had a local maximum, right, at 2, 24. So local maximum at 2, 24. And we know that because that's a critical point where the first derivative is 0 and the slope, which is the first derivative, is going from positive to negative, right? So the function itself is going from increasing to decreasing at that point, and the slope is 0. All right, so we know that's a local maximum. The other critical point that we know of right here is at 5, all right, and we calculated the value of 5, and it looks like that's a local minimum, and we can tell for sure because our slope, the first derivative, is going from negative to positive, right? So there's negative here, positive here, which means it's going from decreasing, right, decreasing to increasing. So we have a local minimum at 5, 4. All right. Now we can actually tell some information about the concavity of f of x as well from the graph of the derivative, right? So the derivative of the derivative, if I look at the slope of this derivative curve, that is the derivative of the derivative. And you can see that the slope during, all during this portion of the curve is negative, right? So that's telling us that the second derivative is less than 0. It's negative. And if the second derivative is less than 0, then it's concave down. Okay, so, which is reflected here, right? You can see that we're concave down all the way from, well, it kind of looks like maybe, this might not be completely accurate. It kind of looks like maybe the slope is about 0 there. So there might actually be an inflection point. This may go more like this. May have a little bit of an inflection point somewhere around here. All right. So, because, here it kind of looks like the derivative is the second derivative of the derivative. The second derivative is equal to 0 about there. Okay. So we may have an inflection point in there. Okay. So then you can also see, let me change colors here. You can also see that here the derivative is increasing, which means, so that, the slope is positive all the way along here, which means the second derivative in this section here is greater than 0, which means it's concave up. And you can see that here. You can see this concave up, the concave upness of it. And I can't draw to save my life, but you can kind of see the concave upness of that portion of the curve. And somewhere in here, it changes, right? It changes the first derivative changes from decreasing to increasing. So it's 0 here. So this is an inflection point. Let's see, I'll put it down here, inflection point. Okay, so we have an inflection point somewhere around there. So if I drop that down here, so you can see somewhere around there, there's an inflection point. Okay, these were critical points. We'll label them CP for critical points, which happen to be local maxima and minima. And so you can get even more information from the first derivative if you look at the slope of the first derivative, which tells you about the second derivative. Which brings us to our next point, which I'm just going to cover briefly here. The concavity. We can tell something about the concavity of the antiderivative. So if capital F is the antiderivative of f, right? Meaning, again, that, let me switch colors here, capital F prime is equal to f, right? So again, f tells us about the slope. So f gives the slope. Lowercase f gives us information about the slope. Slope of capital F, right? Also, if we look at the second derivative, the derivative the second derivative of the antiderivative would be the derivative of f. All right, so f prime gives the concavity of capital F, the antiderivative. All right, so if the slope of f is greater than 0, all right, meaning it's increasing on the interval, so then f is increasing, and the graph of the antiderivative is concave up on that interval. And similarly, if the first derivative of the function that we're integrating is less than 0, meaning that f is decreasing, and that the antiderivative is concave down. Okay, so we saw that up here. We can kind of think of this as the antiderivative. This is the antiderivative. Antiderivative. And this is the derivative, right? So you could see that when the derivative is decreasing, that's telling us that the second derivative is negative, meaning it's concave down, all right? And again, over here, where the derivative is increasing, that's telling us that the second derivative is greater than 0, meaning we have that the antiderivative, the f of x function, is concave up. All right, the notation just gets really confusing here. But you just think it through and you'll get it. It'll take some practice. So that's all I have for this lecture, and I will meet you in class.